velocity v. The object has linear momentum p equal to m times v. Now consider an object of mass m moving on a circle with radius r with constant velocity v. The object is said to have angular momentum equal to m times v times r. Angular momentum describes the motion of an object about some axis of rotation. It's a conserved quantity. The angular momentum that an object has at one time is the same that it has at a later time, provided that nothing else interferes with the object. Angular momentum can easily be demonstrated with the squeezatron, which has a pair of masses revolving about a fixed axis, but the arguments are the same as for one mass. A cord can be pulled within the axis, which changes the distance of the masses from the central axis. Let's start by placing the masses in motion so that they have angular momentum about the central axis. We can then pull the cord, which will move the masses closer to the axis of rotation. Let's first explore our understanding of angular momentum with a pure instruction question. The string on the apparatus will shortly be pulled, moving the masses closer to the central axis. What will happen? Please record your vote on a piece of paper and explain why you chose your answer. Your instructor will now stop the video. Remember that angular momentum is a conserved quantity. Thus, the angular momentum of the masses before we pull the cord is the same as that after. Initially, that value is L equals m times v times r for each mass. As we pull the cord, the radius r decreases as the masses now move on a circle of smaller radius. Since the value of mass m stays the same, how can L remain constant with r decreasing? V has to increase. Doesn't pulling the cord interfere with the mass and change the value of angular momentum? No, and would be something we can do here. But simply consider on the right, note that pulling the cord was a force on it, shown in blue, toward the axis of rotation. Thus, it does not contribute to the motion around the axis. If the force were applied more at an angle, such as for the red force, angular momentum would no longer be conserved. The standard example of conservation of angular momentum is the ice skater doing a spin and pulling in their arms. As more of their mass becomes located closer to the axis of rotation, they must spin more rapidly. In this simulator, we show an object in an elliptical orbit about the Sun. The purple arrow represents the velocity v of the object, while the red dashed line represents the distance r to the Sun. Note that due to conservation of angular momentum, when r is large, the velocity v is relatively small. Conversely, when the distance r is small, the velocity v is relatively large. Kepler's second law is actually based upon the conservation of angular momentum. There are a number of other demonstrations besides the squeezatron commonly used to convey angular momentum conservation, such as a rotating platform. A person sits on the stool holding the dumbbells and gives themselves an initial spin with their feet. The angular momentum level is now established. If the demonstrator pulls in the weights, they will spin much more rapidly due to the conservation of angular momentum. If the demonstrator extends their arms, everything will spin more slowly as the mass is now farther from the central axis. This demonstration is analogous to a mass in the accretion disk falling into a black hole. The three-dimensional version of this demonstration is known as a Hoberman sphere. In this apparatus, a string hangs below the apparatus which pulls the entire structure into a smaller sphere. If we initially put the sphere rotating and then pull the string, it spins much more rapidly. This is similar to what occurs on a larger scale during the early stages of star formation. As a protostar contracts gravitationally, it will rotate more rapidly. When our Sun was at the early stages of collapse, it rotated extremely slowly. As it collapsed down to its present size, its rotation rate increased. When more massive stars near the end of their lives become neutron stars, they shrink down to the size of a city. They then rotate extremely rapidly, up to multiple times per second, sending out beams of radiation along their magnetic axis that appear to us as flashes, all due to the conservation of angular momentum. More teaching materials may be found on the web at astro.edu.